let's skip out these words over here. You can read that later. Let's take this example of the spherically symmetric static metric. All right, we have ds squared is equal to gtt as a function of r times dt squared, plus grr, which is a function of r times dr squared, plus the ordinary spherical symmetry section. Okay, that's the metric that we'll be looking at most of the time when we're doing static situations like we did last time. So now let's do the first calculation. TR. In other words, Riemann tensor R, TR, TR. So you'll have, what we're going to do first is the Gaussian part of TR. Okay? We're going to look at the Gaussian curvature as if this were just two spatial dimensions. You know, TR, just a curved TR surface in ordinary free space. All right? Plug it into the formula. Now let's see, maybe on the side of the paper, if you can take a pen and just work it out yourself without looking at the answer. Okay, just take a few seconds, half a minute. Take a half a minute. This KTR, okay, plug in the values of G and eta that you have over here, and see what answer, okay? Just see this formula over here? ds squared. From that we've got the G's. For the TR curvature, you have T and R. We're talking about the curvature of the TR. You take GT with respect to R, and GR with respect to T. Those are the two, the gamma primes and the gamma primes. So you're taking derivatives with respect to the ones that are in there. The TR is the GT with respect to R, and the GR with respect to T. Right? This is the Gaussian curvature formula in terms of the G's. Here you have the G's. So just tell me what this is equal to. Okay, it's worthwhile doing because this is very important to know. So just figure out what this is given these guys over here.
Figure out what KTR is.
Right. Just in terms of the things that you were given. All right. So basically, we've found what the curvature would be of a two-dimensional surface. Now, what should be the curvature of the TR, considering that it's not really a two-dimensional surface, it's two dimensions of the four dimensions. We have to take into account also this additional term, this gamma times gamma term. It doesn't appear in Gauss's formula. T gamma derivative with respect to R, and R gamma with respect to T, and a product of two gammas, one for the R, one for the T, but only if both R and T have some common coordinate. Do they? Number 5, for the following metric, so in this metric, which coordinates are the intermediary coordinates of which pair? How about the pair, the intermediary terms, the gamma times gamma, contributes only when both of those have derivatives with respect to one particular coordinate, or more than one, but there's a coordinate in common to both of them. So if the GT and the GR both have derivatives with respect to some other coordinate, then there would be an additional term. Okay? That's the contribution that's made by having curvature in a higher dimensional space rather than just this two-dimensional surface. We'll see that again in more examples. So in this particular case of TR, we just have the Gaussian curvature. Tell me why that gamma times gamma term disappears in this case. I'm claiming that it vanishes for the TR curvature. The Gaussian part of the TR curvature doesn't vanish, but this extra additional part, the gamma-gamma part, does vanish. Why does it vanish, given the formula? Okay, given your knowledge of what this gamma times gamma term is, over here, tell me why it disappears for the TR curvature. Okay, again, this is important because you'll kind of be doing this over and over if you solve problems in general theory.
I can maybe guess, but I have no idea.
Okay.
You get educated.
Okay, that's good. You want to make an educate this?
I mean, before on the other page, you see it says IE gamma gamma.
Mm-hmm.
If you look, I mean, it kind of was.
It's that's what it is.
That's
The question
what it
is
is,
why,
right?
that's what it is. The question is why in this case does it disappear? Why is it 0?
Why is it 0?
I'm claiming that it vanishes for the TR curvature.
Constant?
What's a constant?
The coordinates with respect to theta and phi.
Is it a constant? So which one?
The derivative with respect to t. We're
Okay.
looking at the two etas, right?
Right, the etas are just signs. We don't worry about them. We're talking about the g's, right?
But yeah, it's that.
Okay. So go ahead. Which?
That's a derivative with respect to t, right?
All right. So what are the product of the two gammas? Right. You have a gamma times gamma, and you're taking derivatives with respect to a coordinate. Which what? What's the characteristic of this coordinate that you're taking derivative with respect to it? It's not these two coefficients, right? It's not AB. So for the RTR, for the curvature of the TR thing, we're going to sum over which coordinates? Not 2 and 5.
But r
For the TR one, we're going to sum over the things that are not TR. In other words, the theta phi. We're going to take derivatives, in other words, with respect to theta, and a derivative with respect to phi, and take a product. All right? But what are we going to take a derivative of? We're going to take a derivative of the g's which are t and r. In other words, we're going to take gt and gr and take the derivatives with respect to the things that are not t and r. So we're going to have gt derivative with respect to theta and phi, and gr derivative with respect to theta and phi. What are those? It's spherically symmetric, so neither gt nor gr has theta and phi in it, therefore those derivatives are 0. Okay? So because of spherical symmetry, the gt and the gr don't have thetas and phi, and therefore, when you take derivatives with respect to the things that are not in there, the gt and the gr derivatives with respect to not t and r, in other words, theta and phi, those vanish. Okay? Now this is kind of what I call here an intermediary coordinate contribution to the curvature. In other words, the first term, which is the gamma prime, takes gt, takes a derivative, let's say for well, do GRR and GTT have a coefficient in common that's not T or R? The answer is no. The only coordinate they have in common is R, because both the GTT and GRR are functions of R. So they will both have derivatives with respect to R. Right? But in the RT, in the product of the gammas part, where we're looking for a coordinate which is not RT, they won't have. Okay? Does that make sense to most of you, at least those of you who were here last time? Or is it like totally blank?
It was a little fast.
A little fast?
Yeah.
Okay.
It makes sense.
Okay, again, when we do the exercise, all right, we'll do the exercise now, and that'll make it more clear. If you have, let's say, Riemann tensor R for coordinates r theta, so r and theta are the two operative ones. You're going to have a gamma for the r derivative with respect to theta, a gamma for the theta derivative with respect to r, and then a product of two guys. And it's going to be summed over which coordinates? The coordinates that are not r theta, namely t and phi. But only if both of the gammas have derivatives with respect to that coordinate. Okay? To take the theta phi pair, r theta phi, both the coefficient of d theta squared and the coefficient of d phi squared both have a function of r, namely r squared. So they will have derivatives with respect to r. Okay, let's do the t theta. Without looking at it, tell me about the t theta. All right? The curvature of the t theta will have two components. It'll have a gamma prime, two gamma primes really, and it'll have a gamma times gamma. In the t theta, what is the gamma prime composed of? derivatives of what with respect to what?
T with respect to theta, and
T with
theta with respect to
Exactly. T with respect to theta and theta with respect to t. GT with respect to theta and g theta with respect to t. That's the gammas. Then we're going to take the derivatives of those. Again, with respect to t and respect to theta. Now, what is GT with respect to theta? Derivative?
Zero.
Because?
It doesn't depend on theta.
Because it's spherically symmetric. Doesn't depend on theta. Therefore, GT is just a function of r. Has no derivative. What about g theta with respect to t? Same, because
No theta.
no t depends. It's a static. Now, if there was, of course, there would be such a term. What about the gamma times gamma part? What are we going to have in there? What are those gammas composed of? For the t theta?
R's and phi's.
Only r's and phi's. So we're going to have what? G, what derivative with respect to what? Well,
no.
it's a t theta curvature, so it's going to be gt with respect to something that's neither t nor theta, like r or phi, times g theta with respect to the same coordinate. So let's say we have two coordinates, t and theta, so we're going to take derivatives with respect to r and phi. So let's start with r. We're going to have gt with respect to r times g theta with respect to r, plus gt with respect to phi times theta with respect to phi. Okay? We have those two terms. Now, will those terms vanish? First of all, if both of those vanish, then we'd have no curvature. Because the first part vanished, the gamma prime vanished. So we know that those aren't going to vanish. Why don't they vanish? Okay,
And
you're
it's
going to have
gotta be equal, right? And the opposite.
what?
No, oh, I don't, you mean if they equal zero, they vanish?
Right, okay, you're right, they could be equal and opposite, but either way that they vanish, we wouldn't have any curvature, which can't be,
Can't
right.
be.
So you're gonna have the t theta, again, you're gonna have gt with respect to, let's say start with r, gt with respect to r, times g theta with respect to r, right? And they both, in fact, exist. gt has a derivative with respect to r, because it's a function of r, and g theta has an r squared, an r in front, right? So it has a derivative with respect to r. So because they both have derivatives with respect to the same coordinate, that's how that curvature, that's how being in that higher dimension affects it, because it's a t theta curvature, but it's in this r theta phi t. So the fact that both of them have derivatives with respect to r, which is outside their plane, so to speak, gives it a curvature, contributes to the curvature. Okay, so you see that? And then you're going to have the t theta with respect to the phi. You'll have gt with respect to phi, which of course is 0. Right? And then g phi with respect to t, which is also 0. So you're just going to have one term. Okay? That one term there. What about r theta? What's going to happen with r theta?
We just do the same procedure.
Right. So what are you going to get? Okay, so r theta, you're going to have a gamma prime, and a gamma times gamma. What is the gamma prime going to be? What are the gammas before we prime them? For r theta.
Theta and theta r.
So the r theta curvature will be gr with respect to theta, right? Derivative with respect to theta, times g theta with respect to r divided by whatever g derivative with respect to r. Okay? Now, is there a gr with respect to theta?
Oh, is there?
Does it vanish or does it exist? gr with respect to theta.
Zero.
Gr is only a function of r, so there's no derivative with respect to theta. So that doesn't exist. How about the product, the gamma times gamma, for r theta?
Zero.
It's going to be, the r theta is going to be derivatives with respect to which coordinates? If it's r theta? Phi and t. So it's going to be, let's start with t. Okay, so it'll be gr with respect to t, and well, that already is 0. So the t thing is going to vanish, we know, because it's not t dependent. So let's do the phi, did I say? Was it r theta? Right, so we'll do it with respect to phi. So we have r with respect to phi, and the theta, well, that also is going to vanish. So which one remains? Which exists? So we had 4 terms, kind of, like which one? Does any of them remain? Which one didn't we do? The g theta with respect to r. Okay? G theta does have a derivative with respect to r. Okay, what is g theta? Look at the metric. Just r, so just 1. Okay? So that will have, and then, now why doesn't that, if it's 1, why doesn't it vanish when you take the derivative of that? The answer is because you're dividing it by whether it's gr or g theta.
So,
Okay?
so GR with respect, derivative with respect to anything except for R basically is
Exactly.
vanished.
Exactly. And anything derivative with respect to t is going to vanish. Now we want to use all those in the formula. Okay, we want to compute. All right. Now I made a little tabulation over here of those values. The TR is the same as the K. The K is the Gaussian one because there's no intermediate coordinate curvatures. So I just indicated where they were.